All right, what if I told you that one of the most complex, most beautiful images in all of mathematics, a shape with literally infinite detail, comes from a formula so simple you could jot it down on a sticky note? Well, today we're diving deep into the famous, the mysterious, and the just absolutely stunning Mandelbrot set.
I mean, just look at this thing. It looks organic, right? Almost alive. You've got these swirling colors and this coastline that seems impossibly intricate. You'd be forgiven for thinking you're looking at a distant galaxy or maybe something under a microscope. But here's the crazy part. This image wasn't photographed. It was calculated.
So how in the world does a simple little rule generate all of that? An image with a boundary that is infinitely complex. That's the huge question we're going to tackle. And to do that, we first have to understand the canvas it's all painted on.
Okay, first up, the building blocks part 1, the complex canvas. To really get this picture, we have to start with the canvas itself. And that means we're going to have to talk about something called the complex plane. Now, I know what you're thinking. Complex plane sounds intimidating. But trust me, don't let the name fool you. If you remember that standard XY graph from math class, you're pretty much all the way there. All we do is we just rename the axes. The horizontal x-axis, we call that the real axis now. And the vertical y-axis, that becomes the imaginary axis. Seriously, that's it. Same grid, just some new labels.
So, how do we plot a point? Well, it's just as easy as it sounds. Let's take the number 2 plus 2i. The first 2, that's the real part, right? So we just go 2 steps along the horizontal real axis. The plus 2i bit, that's our imaginary part. So we move 2 steps up the vertical imaginary axis. And boom, right where they meet, that's our point.
Okay, let's just make sure that's locked in. To plot any complex number, say 5 plus 3i, you just find the real part horizontally, find the imaginary part vertically, and you mark the spot where they cross. Simple. And here's the key thing to remember. Every single pixel you see in that final crazy image has its own unique address on this canvas.
Okay, building blocks part 2, the cosmic feedback loop. So, we've got our canvas. Now we need the rule. The instruction, the little piece of code that decides the fate of every single point on that canvas. And you're about to see just how ridiculously simple this rule is.
Yep, this is it. That little formula is the entire engine that generates all that insane complexity. It just says z becomes z squared plus c. So what are z and c? Well, c is just the address of whatever point we're currently testing on our canvas. And z? Z is a special number that, for the Mandelbrot set, always starts at 0. That's a key rule.
So think about it like this. For any point C we pick, we start with z equal to 0, we calculate 0 squared plus our c, we get a result. Then, we take that result, plug it back in as our new z, and we do the whole thing again. And again, and again, and again. It's exactly like a feedback loop. All right, section 3, the test. Trapped or escaped. We have our canvas, we have our rule, now it's time to put them together and actually build this thing. For every single point on that canvas, we're going to apply our little rule and ask one very simple question.
And this is the test. For each point C, we ask, as we keep running our little feedback loop, does the result just get bigger and bigger and bigger, basically flying off to infinity? Or does it stay trapped, just kind of bouncing around close to where it started? That's it. Every single point on the canvas is going to do one of those two things. No exceptions.
Okay, let's actually see this in action. Let's test the point where c equals 1. We start with z equals 0, right? So 0 squared plus 1 equals 1. Easy. Now our new z is 1. So 1 squared plus 1 equals 2. Now z is 2. 2 squared plus 1 equals 5. The next one's going to be 26. You can already see the numbers are growing, and they're growing fast. This point is definitely flying off to infinity, so it escapes.
But now, watch what happens when we pick c equals -1. First step, 0 squared minus 1 equals -1. Okay, now z is -1. So -1 squared, that's +1, minus 1 equals 0. Now z is 0. So 0 squared minus 1, we're back to -1. And then we'll get 0 again. You see, it's just stuck in a loop forever. It can't go anywhere. This point is trapped.
Next up, the big reveal, a map of infinity. Okay, so we've established that every single point on our complex canvas is either an escaper or it's trapped. We have all our test results, so let's put it all together and finally see the masterpiece.
And here is the final beautiful step. It's basically like a cosmic coloring book. The rule is simple. If a point is trapped, we color that pixel black. That main black cardioid-looking shape you see, that is the Mandelbrot set. And what about all the other points? Well, if a point escapes, we give it a color based on how quickly it escapes. The ones that zoom away get one color, the ones that hang around for a bit before taking off get another.
And there it is. This is the big aha moment. On the left, you see the basic idea, right? The black trapped region surrounded by all the colored escaped regions. And on the right, that's what happens when a computer runs that simple test for millions and millions of points. This isn't a drawing. It's not art in the traditional sense. It's a map of the behavior of that one tiny formula. But the real magic, the thing that makes this set so famous, lies in the boundary, that coastline between the black part and all the colored parts. As Wikipedia so perfectly puts it, this boundary is, quote, infinitely complicated.
So what does infinitely complicated even mean? It means you can zoom in on that edge forever, and you will never run out of detail. You just keep finding these strange, beautiful new worlds. There's a famous part called the Seahorse Valley, for example, where you find these intricate spiral patterns that just seem to repeat endlessly. And as you dive deeper and deeper, you realize it's not just random squiggles. You find structure. You start to see these tiny, kind of distorted copies of the entire Mandelbrot set just floating there, like little satellites around the main body. And guess what? Each one of those tiny copies has its own, even tinier copies inside it. The pattern just echoes itself on smaller and smaller scales, literally forever.
All right, our last section, why it matters, more than a pretty picture. So, okay, it's beautiful, it's infinite, it's an amazing thing to look at. But why does it actually matter? What's the big takeaway here?
Well, the Mandelbrot set is so much more than just a pretty picture. It's a foundational object in chaos theory. You know, the study of how tiny little changes in a simple system can lead to these wildly different, totally unpredictable results. It's the butterfly effect, visualized. This set is a perfect picture of that idea. But maybe most of all, it's this profound example of something called emergence. This idea that incredible, infinite complexity can just appear from the absolute simplest rules. And not just in math, but maybe in nature itself.
And that leaves us with a final, really fascinating thought. See, the Mandelbrot set wasn't invented. It was discovered. It was always there, just waiting inside that one tiny little equation. And that just has to make you wonder, what else is out there? What other infinite, beautiful universes are hiding in the simple rules that govern our world all around us?